Right. Hello, everybody. Welcome back to another video. And in this video, we're going to be doing a paper 2 question. Wow, I know, right? It's been a while. Usually I do the MCQs, but this time I'm going to be doing a paper 2 question. And the reason why I actually do the MCQs is because I feel like students who are solving the MCQs, often the MCQs require you to actually know the concept very well. And in the mark scheme, they don't give you an explanation behind the answers. They just give you the letter or the correct option. And then you kind of left blank with, oh, why is it that? But I feel like in paper 2, IB does a slightly better job with the mark scheme and they give you some explanation behind it. But I found that this particular question, they actually don't give you any explanation behind why it is that answer. And in a way, it makes sense because I think the mark schemes are meant for the teachers and not for the students. But anyways, I will be attempting to explain why a certain answer is the correct answer for these questions, and I'll also be solving it alongside you. So hopefully this video helps you, and let's get on with the question. So this is question number 2. Compound A is in equilibrium with compound B. So we can see over here that an alcohol is being converted into a ketone. So this is an oxidation reaction, which is unnecessary for this, but just additional information for you. So they've asked us, predict the electron domain geometry and molecular geometries around the oxygen atom of molecule A using the VSEPR theory. Okay, so now if you don't know what VSEPR is, you are going to be very, very confused in this. So I will highly recommend you to go back and revise this before you watch this video. So anyways, the first is electron domain geometry. Let's take a look at oxygen. Let's take a look at oxygen in molecule A. So we have an oxygen. It's attached to a hydrogen to form the hydroxyl group, and then this oxygen is attached to a carbon. Now, if you're confused what these lines are, this is actually the skeletal structure which is often used to draw organic compounds. And essentially, each intersection point between two lines is a carbon, is signed for a carbon. So the ends of two lines is a carbon. So supposing if you have a double bond, like in the structure over there, you have something, it looks something like this. And then over here, so there is a carbon here, there's a carbon here, there's a carbon there, and over here you have an oxygen attached. So this is what the skeletal structure looks like, or what it represents. And the hydrogens are also attached, but I'm not going to draw that for this sake, for this diagram sake. So just take a look at this oxygen. We can see that it is forming two bonds, and that means that it is engaged, or two of its electrons are engaged in bonding. And that would leave 4 electrons which are not engaged in bonding, and these would form the lone pairs of electron. So these would be over here. These are the lone pairs of electron. And now for the electron domain geometry, literally all you have to do is count the number of bonds that the atom is making. So in this case, oxygen is making 2 bonds, and so it's 2 bonds, and then you have to count the number of lone pairs. So it has 1 and 2. So there are 2 lone pairs. And this means that it has 4 different electron domains. And why are the lone pairs counted as a domain? Well, that's how it is. Each lone pair is counted as an electron domain. Now, I don't know exactly why they're counted as an electron domain, but you could go ahead and research that. That is slightly out of my expertise. So since there are 4 electron domains, the electron domain geometry is considered as tetrahedral. Now, that's why if you don't know what this tetrahedral or what electron domain geometry is, you should go back and study the VSEPR theory, because without without knowing that, all of this will just be gibberish and just end up confusing you. So please go ahead and do that. So it will be tetrahedral. Now, the molecular geometry. Now, the molecular geometry is slightly more tricky than the electron domain geometry. Now, in the electron domain geometry, all you have to do is count the number of lone pairs and count the number of bonds that are attached to an atom, or actually number of elements which are attached to an atom. Remember, if supposing, just imagine there was a double bond, which is not possible, but just imagine there was a double bond over here. This double bond will still be counted as one electron domain. So instead of bonds, actually, I should rather be saying the number of elements which are bonded to oxygen. So count the number of elements bonded to oxygen and count the number of lone pairs. Anyway, so now that is how you find the electron domain geometry. But the molecular geometry is slightly more tricky. In addition to considering the lone pairs and the number of atoms bonded to the oxygen atom, you also have to consider the shape and the orientation that the lone pairs and the bonds will result in. So what I mean by that is that even though even though the shape looks like this, I'm drawing the element like this, they actually might look quite different in real life. So these lone pairs over here, they cause a lot of repulsion. They repel the bonds. So these bonds kind of get pushed together. So these lone pairs repel the bonds. They don't like them. And they might push the bonds together like this, something like this, because of the repulsion. So they get bent. Now this shape is different to what the shape would look like if you just drew it like this, right? Because this one is slightly, it's more compact, it's more bent because of the repulsion caused by these lone pairs. So that's what this repulsion and the change in shape should also be accounted for when determining the molecular geometry. And the molecular geometry of such a shape is called, well, by the looks of it, you can call it bent. That's the molecular geometry, or V shape, because, well, it looks like a V. So this is the molecular geometry. And if this may ring some bells for you, it actually looks a lot like the molecular geometry of water, which looks like this. Just give me a second, let me draw it out. So this is the molecular geometry of water. So again, it's the same case. Oxygen has two lone pairs, and this repulsion caused by the lone pairs causes the water molecule to be bent or V-shaped, just like our element over here. So the molecular geometry is bent, or if you prefer the other term, you can write V-shaped. But in the exam, I would recommend you to only write one of them. I don't think you should write both, because that might confuse the examiner, or it might make you lose marks, even though both are the right answers. Now, the next part, B. State the type of hybridization shown by the central carbon atom in molecule B. So the central carbon atom in molecule B, in order to do this, you first have to really draw out the proper structure, not the skeletal structure. You have to really expand the structure now. So let's expand it. So in terms of skeletal structure, molecule B looks like this. So now if you expand this, and if you draw the carbons and the hydrogens and everything that's there, it would look something like this. So now the central carbon atom is this carbon right over here. Now, in order to determine the type of hybridization, first we have to count the number of electron domains that are present around the central carbon atom. So we can see that there is one electron domain, two electron domain, three electron domains. Now, remember, a double bond or even a triple bond is still considered as one electron domain. It is not considered as two or three. Triple bond, single bond, double bonds are all considered as one electron domain. So in this case, carbon has three electron domains. That means it will need three hybridized orbitals to engage in bonding. That means that the hybridization will be sp2. And this sp2 quite literally translates to s times p times p. And there's 1, 2, 3 hybridized orbitals which are available for bonding. So that's why it's called sp2, because it's s times p times p. So this is actually like p squared. Now, I'm going to show you an easy trick to figure out the hybridization of any central atom or any atom that they ask you to determine the hybridization for by just looking at the number of electron domains that that specific atom has. So if that atom has 2 electron domains, the hybridization will be sp, because it only needs s times p. It needs only 2 hybridized orbitals. If it has 3 electron domains, like what we saw with the central carbon atom in molecule B, it will be sp2, because it needs 3 hybridized orbitals to engage in bonding. Now, if it has 4 electron domains, it will require sp3, because it needs 3 electron domains, or sorry, 3 hybridized orbitals to engage in bonding. So now that is it for this video. I hope that it has helped you. I hope that I've slightly cleared up any concepts that you may have been confused with. If you have any questions about this video or any concepts discussed in this video or any other video, please let me know in the comments or send me a message on my social media or send it to me via email, and I'll be more than happy to help you. Thank you so much. I'll see you in another video with a new question.